and we're going to go into the second part of the lecture, which is going to be the data definition part of SQL. So we looked at the data manipulation part, the data manipulation language, because we looked at selecting, inserting, deleting, updating. So now we need to understand how do we actually create the objects that we're going to insert the data into, the tables, etc., the attributes, and so on. So how do we actually build the database in the first place? Are we all ready? Good. So we're going to look at the use of SQL for data definition as part of this lecture, and hopefully by the end of it you will be able to write data definition language statements. When it comes to your coursework, the first part of it will be writing this type of data definition language statements. So what happens is I will give you a set of table definitions which won't have primary keys, won't have any check constraints, won't have any of the definitions, and you'll have to make those yourself. And this will be assessed. So you'll need to know how to do all of these things. Then you will go on to populate the tables with insert statements. Then you'll go on to do data manipulation statements. So that is what your coursework is going to look like. And this is covered in Connolly and Beck chapter 7. We've actually covered quite a little bit of the book already, if you have been reading the book, which is what I said you should be doing. So hopefully you will realize we've moved along quite a long way already. We are already halfway through the course, isn't it? Week 6 today. So more than halfway, because week 12 we don't have a lecture unless you want to have a revision lecture. So that is good going. And what we're going to look at now, as I said, is how we do the data definition language. So when we talk about, and that reference to DB2 I should change, because that's how we used to do DB2, now it's Postgres. So change that in your notes. But if we have a Postgres or a DB2 DBMS or an Oracle DBMS, what we generally have is an environment defined, which in our case will be Postgres SQL instance on the server. Then, as well as an environment, we might have catalogs defined. So, for example, one for one course, like 2B08, one for another course, like MB11, and so on in our case. We, within those catalogs, may have schemas defined. And the schemas are going to hold a particular database. So I might have a schema, as you have seen, for the demo database that you use in the labs, another one for the date database that I use when I do the lectures, and so on. So these are different schemas defined. Some SQL environments allow you to define domains as well. Some others do not. If you don't have domains, then you just use the data type and check constraints to limit the range of values that a particular attribute can take, or the type of values. You might also have tables. So, for example, an emp table, which you see in the labs, a task table, which you see in the labs. You then have columns or attributes as well, which are emp ID, hourly rate, etc. You might have views defined of those, which we will look at as we proceed with the lectures. And we might also have indexes, which are part of this internal kind of like schema, internal definition, to speed up the queries. So these are the type of objects that we're going to handle when we talk about the data definition language. Now, the Postgres SQL instance and the databases are created by the database administrator. You will have no permissions to do that. So you cannot create new environments, you cannot create databases. That has to be done by the database administrator. You can create schemas, you can create tables, you can create views, but not the higher objects. Okay? So those are the things that we are going to look at. The others require privileged software tools to be allowed to create. So if you want to create a database, you need to have a special privileges as a systems or a DBA administrator. So what we're going to look at in SQL is how we create the schema, how we create the table. We won't look at how we create the domain. It's possible, but we don't worry about domains. We look at the check constraints and how we create particular attributes as data types. We look at how we can create views, indexes, and for all of those objects, if we want to delete them, we can use the drop command to delete that particular object. And we can, to a certain extent, modify objects that already exist. And that will be through the alter command. Okay, so those are the things that we need to understand in this lecture. So the first thing that we might want to do is create a schema. And a schema is going to be the place where we hold tables that are kind of like interrelated. So if you were going to do your coursework, you might want to create a schema that defines a particular piece of coursework, and it has different tables associated with that schema. So to create a schema, we can say create a schema demo, for example, if I wanted to create a schema demo that you use in the labs. Then, once I have a schema, I can associate particular tables with that schema. And to do that, I can say create table demo.emp. So if I qualify the name of the table with the name of the schema, then it's a table created in that particular schema demo. Once I have created a table, I can then insert into that table with the insert command that we just looked at. So I can then say insert into demo.emp a set of values. And once I've inserted, I can select, which is what we learned in the previous lecture. So I can create the object. Once I've created the object, say the schema, I can associate tables with it. Then I can insert values into those tables. Then I can select from those tables. Or I could set, in this case, set a schema demo in PostgreSQL is slightly different because you have to use a command set search path to demo.public in the specific case of PostgreSQL. Once I am in that particular schema, I don't have to then qualify every table name with the name of the schema because I'm working within that schema. So if I then say create table M, it will be created within the schema demo because I'm already working in that schema. So I can either work from the default schema which is associated with your username, or I can work from a particular schema that has been created, and then the objects that I create there will be associated with that particular schema. The PostgreSQL is going to assume your default schema, which is your user ID. So that is going to be a default schema. Anything that you create, if you don't go to another schema, is created there, but you can create additional schemas, then set search path to be that, and then you will be in that additional schema. As well as creating schemas, we can drop them. If we drop them, we delete them. We delete the schema and every object associated with it. So if the schema has tables, they will also be deleted. Now, we can drop a schema demo with the word restrict, and that means that that will only be dropped if it has no associated objects. So if I execute this, and demo has some associated tables or whatever other objects, then the deletion will fail. So it won't allow me to drop the schema if it has associated objects. If I said drop a schema demo cascade, it will then delete every object associated with that schema. So you have to be careful that if you cascade the delete, you're deleting everything that is indexes, etc., that have any association with that schema. If you restrict, then that deletion won't take place if there are any objects that are associated with that schema. Okay?
In the top table, on the bottom line, I didn't quite catch why you've got demo.emp.hourly rate, and then why you need to define which table it's from.
Select demo, because I'm saying demo.emp, demo is the schema, .emp is the table, and hourly rate is the particular attribute I want to select.
Why then have you got the next three words? I don't get that.
Where?
Why do you need to put from demo.emp? If you've already written demo.emp.
Yeah, you probably don't need to.
You don't?
Yeah, you probably don't, but you can. Right, so the next thing that I might want to do once I have defined a schema is define a table within the schema. So if I want to create a table for suppliers, I can say something like create table S, so I give it a name, and then a series of attributes, and for each of them I need to give at least a data type. So in there I'm saying this table S is going to have 4 attributes. The first one is a number, which is a character, and it's a fixed length. So it's a fixed length 2. That means that 2 spaces will always be allocated to that particular attribute, whether they are used or not. S name, again of fixed length 6, which might not be very realistic, but if I do that, then 6 spaces are allocated to the name. Status I might call a small int. We'll look at the data types in a minute. And city, again, could be something like fixed length character 6. That is a table, is not a relation. It only becomes a relation when we provide a primary key, because without it we could have duplicate tuples, and that we know is not conform to the definition of a relation. So therefore, at the moment we have a table. When we add a primary key and possibly candidate keys, it becomes a relation, because then we have defined that tuples have to be unique. So we have to do that. The primary key is going to allow us to enforce this entity integrity. Who can remember what entity integrity was? Don't disappoint me. I'm going to begin to cry otherwise. What is entity integrity? There were two things, entity integrity and referential integrity. And entity integrity said, yes, at least one person knows this. Good. So the primary key, no part of the primary key can be null. So once we have said that in this case this number is not null primary key, we probably don't need to even say not null because the primary key is going to enforce that. Then we know that we can enforce entity integrity, no part of the primary key can be null. Then we might also define a candidate key. If we wanted to define a candidate key, another thing that uniquely identifies the tuples, then we could refer to it as unique. So that identifies a candidate key. It tells me that this name is also going to be unique in this table because I've put the word unique next to it. I'm not using it as the primary key, but it's a candidate key. And for the rest, for each of them I have a not null constraint, and that means that I'm not going to allow any null values in that table under any circumstances. I might or might not define them as not null, but if I put the word not null, then I'm always going to have values associated with these attributes. So the next thing in terms of integrity constraints was the domain integrity. We said that every attribute has to have a domain which might or might not be well defined depending on the attribute. If it's well defined, we can then put some constraints of the values of the attribute that the attribute might take. So here we have, for example, the table S, and we're building up this data definition for it. So now we have S number, which has defined as the primary key, S name, a status, and now we want to have a check on the status, because we know a status can only be between 0 and 100. So we can define a constraint to do that. So when we want to constrain a particular attribute value, we have a check constraint. And we can say check status is greater than 0 and status is less than 100. So it won't be able to be 0 or 100, but it will be a value between 0 and 100. And I could also have another constraint on the city that says it's not an empty string. So I'm not allowing an empty string, not a null value, but just a string of blanks to be associated with the city. So I can begin then to build up with that domain integrity, because I have the power to define check constraints on the attributes. So that's another part of your coursework. I won't give you any check constraints, but whenever possible, you should define your domains as well as possible, because that guarantees that the database will be consistent and it won't have values that it shouldn't have. So if there is a possibility to define a check constraint, then do so. Then we have the not null, which is required for the primary key, because we want our primary keys not to be null. But we can also have that, as we see, for other particular attributes. As well as that, we might be able to set defaults. And the default will be the value that is taken in the absence of other values. So if I am going to insert for a particular attribute, and I have no value, but the default has been defined, that is what will be put in a particular record. So I can define default, so I could have, for example, mark, small int, default 0. So whenever I enter marks, if I don't have a value that is being entered, then the mark of 0 will be entered. Equally, I could have something like a status, varchar 20, and if I say varchar, it means it's of a variable length character, so it's up to 20 characters, but it might not necessarily use up to 20 characters. And the default is undergraduate. So that means that whenever I don't have a value given for a status, then the default value will be given to that particular tuple. So I can do that. And the next thing I might want to do, again, another important thing that you have to do when you do your coursework, is to define the referential integrity constraints. So somebody is going to tell me what referential integrity was all about, because you do remember. So what was referential integrity all about? Don't depress me again. Make me happy, it's a sunny day. What was referential integrity about? We had entity integrity, we said every part of the primary key cannot be null. And then we had referential integrity that said,
Is it to do with the lengths of rows that will be in the same table?
the referential integrity had to do with the foreign keys, and it says,
every foreign keys must be a reference to a primary key in another.
exactly. See, some people were listening. If we have a foreign key, then it must be a reference to a candidate key, a valid reference to a candidate key in another table, or it must be wholly null. Okay? So if we have a foreign key defined on a table, which references a candidate key or the primary key of another table, it either has to be a valid reference, that means that a value exists, or it has to be wholly null. Now, if you don't know these things by now, you really need to read about them, because that's one of the key issues to a relational model. So how do we ensure that when we're defining a table? We have to write referential integrity constraints, because we have to make sure for any model that is a relational model that we absolutely enforce entity integrity and referential integrity. Remember that was how we kept the model whole. So I have defined my entity integrity because I've defined my primary key. And what I want to do now, and in this case my primary key, by the way, is a combination of fields, so I define it separately, and I say primary key is S number and P number, so it's a combination of those. Any constraint can be named. You can name them, and that means when an error in SQL is generated, it will be associated with the name that you gave the constraint instead of a system name. So sometimes it's a good idea to name your constraints, because you will get an error that will relate to the name that you gave it. So in this case, I'm naming my constraint, and I call it SPPK. So when I get an error referencing that particular constraint, for example, I try to enter a null value, then it will say that this particular constraint by name has been broken. So I get a reference to the constraint name. I could also name my foreign key constraints if I wanted to. Okay, so you can name any, and the check constraints you can name as well. You can name any constraint that you like if you want to get your errors to reference a particular name. Otherwise, they're given a system name, which is what you see when you see an error. So I want to define my foreign key, and in this case, I know that S number is my foreign key in this table, and it references the supplier number in the supplier table. So I want to make that link in the table. So I say foreign key S number references S. That is going to enforce referential integrity. So it means when I try to insert into this table, the system will make sure that the reference, the S number that I am inserting, is a valid S number in the supplier table, because I've made that constraint. Equally, I can also say here what happens when I try to delete. Remember that when we did the seminar, if you did go to the seminar in question, should know everybody, we talked about this. We talked about what happens when we try to delete something which is referenced by something else. So what happens if we try to delete a supplier which has shipments? If we don't do anything, if we delete the supplier and we leave the shipments, the reference becomes invalid, because the shipment will reference a supplier that no longer exists. So we've broken referential integrity, unless the supplier number was defined to take nulls. Now, in this case, it said not null, so I couldn't possibly have a null value in the shipment table. So if it cannot be null, then I have to decide what to do. So if I say nothing, the default is on delete restrict or no action, which means that the deletion is not allowed if the supplier that I am trying to delete has shipments, then that deletion of the supplier is not allowed. And that is the default. So if I don't specify anything, that is what happens. I can specify on delete cascade, on delete set to null, on delete set to default. Okay? If I say on delete cascade, if I delete a supplier that has shipments, every shipment is going to also be deleted because I'm cascading the deletion. So I'm dealing with referential integrity. And I have to do the same for the foreign key P number, which references the P table. I got to specify it references the P table. If I say nothing, then I mean on delete restrict, or no action, which means I'm not allowed to delete a part if it appears in the shipment table. Do we understand that? Because if you don't understand that, you are well and truly bleep. I have to say bleep because I'm being recorded. I don't want complaints. And apparently I have an audience, I've been told, in Afghanistan and some other very foreign countries that are listening to my lectures. So we don't want to offend anybody. I don't know why these people will listen to my lectures, but hey, maybe it's fame at last. So maybe if I ask them the questions, they'll be able to answer better than you. And that should be sad. So now we're going to think about referential integrity in terms of the actions that we can have. We can cascade the deletion, and that means that if I have a supplier which has shipments, if I say delete cascade, all of the shipments associated with the given supplier will be deleted as well. You have to be very careful about doing this because you could delete a whole lot of data unintentionally. So you can only use on delete cascade if you're very sure that this is the right action to take when you delete a supplier. Alternatively, you can set the foreign key to null if that is allowed. In the previous table, we defined S number to be not null, so we couldn't set it to null because it doesn't take null values as we have defined it. We can set it to a default value if a default value has been set. We didn't have a default value, so we couldn't do that. And we could have no action or restrict that do the same. And that means that if I try to delete a supplier which has shipments, the deletion will be rejected by the system. I have to first deal with the shipments and allocate it to another supplier, then I'll be able to delete it. Do we all understand that? Here and in Afghanistan and whatever other countries might be listening? Okay. So, in PostgreSQL, which is what you're going to be handling, you have on delete no action, which is the default. So if you don't say anything, it's no action. And restrict. Now, no action and restrict are more or less the same. You can consider them as being the same. The difference is between them is where the DBMS is going to check other constraints. So they do the same, but in one case, some checks will be deferred until the end of the transaction. In the other case, the checks will be done initially. But at the end of the day, to all intents and purposes for you, they're going to do the same. That means the deletion will not be allowed if you have objects that reference that particular object. You have cascade, you have set to null, and you have set to default. And on update, you can also specify the action. So if you're going to update the supplier number, what do you want to do with all the tuples that are referenced by that supplier number? So you can have the same actions. You could say no action, restrict, set to null, cascade, and so on. Okay? And as I said, note that all of the constraints that you have, whether they are referential integrity constraints, check constraints, primary key constraints, they can be named. If they are named, you can reference them by name. You will see them coming back when there's an error by the name that you've given them. So what about deleting once you have a table and you want to delete it? Now the command for deleting a table is drop table S. When we saw the delete command before for tuples, if we delete a set of tuples, even if we say delete from P and it deletes all of the data, the table definition is not deleted. What is deleted is the data. But the table definition stays, and we can enter new data into that table because we haven't dropped the table. If we drop the table, we drop the table definition. The table no longer exists for us to enter data. So one thing is to delete the data, another thing is to drop the table. If I drop the table, I get rid of all of the attributes and any check constraints, etc., all of the objects that are associated with the table. So drop table S and like delete from S is going to delete all of the table definition or the associated definitions. And we can have it with restrict and with cascade. If I say with restrict, if there is anything in that table, like data, or then it won't be allowed. If I had it with cascade, all of the objects that are associated with the table will also be deleted. There is a possibility to alter a table slightly. So there are some things that we can do without having to drop the table and recreate it. Sometimes if you have to make major changes to a table, it might be easier to just drop the table and recreate it. But if you have to make minor changes, there is an alter table command. And it allows you to modify tables to a limited degree. You can add a new column. You can drop a column that exists. You can add a new constraint. You can delete a constraint that exists. You can add a default. You can delete a default that exists. So those are the things that you can modify with the alter command for the table. So I could have something like dropping a default, alter table stuff, alter position, drop default. So that is going to modify the table stuff. It's going to take the position attribute and drop the default associated with it. I could add a new default, so I could say alter table stuff, alter sex, set default to F. So I'm adding a new default to that table without having to recreate the whole table definition. I can drop a constraint, so I could say alter table property for ren, drop constraint, and I've named my constraint, so now I can drop it by name. So that is the name I gave my constraint. Or I could add a new column, alter table P, add stock quantity, integer not null. If I add a new column, I have to give the data type associated with it. Okay? Happy with that? So now, a little bit on the data types that you have in Postgres. Obviously, the data types are going to vary slightly from system to system. Different systems might define them slightly differently. But you have things like a small integer, which is only allocated 2 bytes, and therefore allows you to represent the small integer numbers from the range minus 32,000 to plus 32,000. We can have an integer, which is allocated 4 bytes, so we can have slightly larger range of numbers that can be represented. Or we can have big integer, which has 8 bytes allocated to it, and therefore gives us an even greater number. Obviously, we want to be reasonably conscious of the storage space, so if we only need a small integer, we'll use a small integer, because if you have a large table at the end of the day, who is trying to pair up with me? Please. What an interaction. Somebody with a Bluetooth device here for sure. Okay, so we have decimals, which have a variable amount of storage, and numeric, which are also variable, and they have user-defined precision. There is no limit to the numbers you can represent. You have real double precision. Real have 4 bytes, double precision have 8 bytes, and we can have up to 6 decimal digit precision or 15 decimal digit precision there. And then you can have serial and big serial if we want to have auto-incremented numbers. For example, for a primary key, we wanted to use something that auto-increments, we could do something like that. As well as those which are the numeric types, we have character, varying, and bar chart, which are the same. And there you give the length that you want to allocate. So this is going to be up to that length. Or we have fixed length character, which are character n or char n, where I have to say how many characters I am going to represent, and the computer will always allocate that storage. And we have text, which is unlimited length variable. So if I define it as text, then it's unlimited. I also have timestamp, which is going to be a composition of both the date and the time. And I can then separate them. So I can have a timestamp without the time zone, or the timestamp with the time zone. I can have date and I can have time separately. They both make up the timestamp. And I can have time without the time zone and time with the time zone if I want to store it. And I can also have intervals of time defined. So those are the kind of data types that I have for dates. And then the last thing that we need to cover is indexes. Now again, indexes are not quite well defined in the SQL standard. As you know, we use them when we want to speed up queries. So we want to, once we have a database in use and we see that particular predicates are very much used, or particular keys, or particular joins are made, then we might want to define indexes to speed up the queries. So you should see some of this when Dan comes to talk to you about the kind of physical design and the physical storage and so on. So we're going to use them to speed access to rows in a table, because if we define an index, it's a bit like having an index in a book. You know, you don't want to look through every page. You can go back at the index and find out this reference is in page 467, so you quickly go there. An index is a bit like that. It gives us fast access to something that has been pre-indexed. And again, there DB2 should be Postgres, creates indexes for primary keys and unique columns. You might also want to create other indexes to support things like foreign keys, if they're not automatically done. Other joins that you might do, common query predicates. So if you're going to, for example, query by surname, you might want to create a surname index, as well as perhaps query by student number and so on. So we can have unique index if the field that we're trying to define the index on has unique values. Then we create a new index. For example, pname index on pname, supposing that the pname is unique. Or we can create clustered indexes where there might be more than one value of the same. So for example, city index on p city descending. So I can say whether I want my index to be ascending or descending. And equally, as I create index, I can drop them, like I can drop other objects. So if I drop index city IDX, then that index that I created is deleted, and it's no longer there. So this is, for example, a simple data definition language program to create the data schema. So the first thing I might want to do is create a schema date, where I'm going to put my tables. Then in PostgreSQL, I have to say set search path to date public, so that I don't have to preclude every table name with a schema name. Having done that, I want to create the supplier table. So I say create table S, and I have S number, S name, status, city, and a primary key. I then have the parse table, where again I have P number, P name, color, weight, city, and the primary key. And then I might have the shipment table, which has S number, P number, and quantity. For that, I have to have a primary key and two foreign keys. S number which references S, and P number with references P. Since I have no say on the delete cascade, it is assumed that it's going to be on delete, no action on restrict. That means I'm not going to be able to delete a supplier if it has shipments, and I'm not going to be able to delete a part if it appears in shipments. I have to first delete the shipments or rename them, give them a different supplier or whatever. And then I might create some indexes. I could create an index on the city name, on the supplier city, on the part city, on the S name, on the part name, if I thought that these are predicates that I am going to.
Is using IDX, is that quite standard usage? And then you
Well, you can name them like that because it kind of like sounds like an index, but
I think it's a standard term.
I think, I don't know, but I think if it's, you know, if they will, you have to name them in a way that you will know what that object is, and I think if you use IDX, it probably is giving you an idea that that's an index. But I don't know if it is a standard. Index in general not standard in SQL anyway, so they are slightly kind of like outside of what is the defined standard. So another little problem for you. Create a table called department with the following columns: a department number, which is a unique 5-character code which identifies a department; a budget, which is a decimal amount up to 99,999.99, which must be positive; and all departments must have budgets. An allocation, an optional description of up to 30 characters. So how do we do that? I'm going to have to do it on the bottom because I have nothing to clean the thing with.
Create.
So we have create table. What's the name of our table? Department. And then we need to have the set of columns that we're going to have. And the set of columns are, let's say department number, what type do we make that? 5 character codes. So it will be char, yeah, char 5. So that will always give it 5 characters. Yeah, it's unique, and in fact it's going to be the primary key, isn't it? So I think we could just say primary key, because that then identifies it as a unique thing. Then budget, and the budget is what? Sorry? Integer? Or decimal? Yeah, because if it is integer, we cannot have the decimal point. So decimal. And then it says, and sometimes we can specify for a decimal the precision, which is the number of digits before the dot, and then the scale, which is the number of digits after. So in that case, we will need 5 and 2. And then we have, it says it must be positive. So how do we guarantee that? Check constraint, check. And what do we check? Budget must be greater. Does it say can it be equal to 0? No. Positive. So positive is 0 as well. So greater or equal than 0. Okay. And then it says up to 9999. 9.99. So we need to include that as well. So we'll have to say and budget less than or equal to 99999.99. So one of them is going to be defined within those. So we're given it. And it says all departments must have budgets. So what does that mean? Not null, yeah, because we must have a budget, so we cannot have a null value there. And then we have location, an optional description up to 50 characters. So we have location. How will we find it? Varchar, because it's up to 40 characters or 30 characters. And it's optional, so we don't have to have a not null, because there might or might not be a location. And there's nothing we can say about it in terms of check constraint, because we haven't been given a check constraint. So that is our table for the department.